Remote Control Conveyor Belt Final Presentation Group 6.
In industry, goods or materials are required to be moved within their working environment. Implementation of an automated conveyor belt system improves efficiency, saves time to better utilize human effort, as well as decreases the likelihood of human error or injury. This project description is to design a user-friendly, robust, and well-controlled automated conveyor system and user interface which can communicate wirelessly whilst implementing key components such as the Arduino Uno microcontroller, Bluetooth module, H-bridge, and DC motor. Objectives: 1. Design and coding of a user interface which allows the selection, editing, and setting of input parameters. This includes allocating input parameters as variables to be sent via Bluetooth, displaying set parameters on an LCD, implementing a start-stop button, implementing LED operations. 2. Design and coding of the conveyor belt system which allows operation at a desired speed, direction, and mode of control. This includes allocating possible operation options as variables according to that set at the user interface, receiving inputs via Bluetooth, implementing a PID control mechanism to maintain desired input parameters, displaying actual operation parameters on an LCD, implementing push buttons to view actual parameters and an emergency stop button, implementing LED operations. 3. Pairing of HC05 Bluetooth modules and setting modules as master and slave devices. 4. Design both user interface and conveyor system to be sturdy, presentable, and user-friendly whilst considering sustainability. Literature reviews, all referred to in references. 1. PWM control of a DC motor used to drive a conveyor belt. A journal article by Petru and Gandur. Researchers set up an experiment to determine the effectiveness of using PWM for speed control. They used an Arduino Uno microcontroller to generate a PWM signal to control the speed of the motor and hence the duty cycle. The speed of the motor and the corresponding duty cycle was measured in both directions. They concluded that the relationship between the motor speed and the duty cycle of the PWM signal had a fairly linear relationship and hence using the PWM technique to control motor speed would be suitable. 2. On power and throughput trade-offs, a journal article by Friedman and colleagues. Researchers conducted a study on the power consumption of Bluetooth versus Wi-Fi. They did this by connecting a smartphone to a circuit with a resistor and measured the voltage across it. They used several different smartphones as well as tested it in sending and receiving mode for both the wireless communications. They found that the data transfer rate was much higher for Wi-Fi. However, this resulted in a power consumption almost 2 to 3 times that of Bluetooth. Hence, Bluetooth was seen favorable for our application. 3. Implementation of a PID control system on microcontroller. A journal article by Mohammed and Abdallahs. Researchers conducted an experiment to investigate the effectiveness of using PID control to maintain a set point for DC motor speed. They did this by simulating a PID-controlled DC motor using MATLAB Simulink. They then constructed a physical system similar to that simulated one, using Arduino Uno microcontroller as the PID controller. Researchers measured the steady-state error, rise time, and settling time for both systems. They concluded that both systems were effective and managed to meet the requirements of having a steady-state error of less than 5%, rise time less than 2 seconds, and settling time less than 4 seconds.
To successfully complete the objectives of the group, an operational model had to be developed, which is represented by the block diagram on the left. This system contains two subsystems, which are the control panel, which is the master device, and the conveyor belt, which is the slave device. In the control panel, the master Arduino is powered by a 9-volt DC signal and has input devices such as 6 push buttons and a potentiometer, and output devices such as LEDs and an LCD. This system controls the conveyor belt system. In the conveyor belt system, the slave Arduino is powered by a 9-volt DC regulated signal from the power supply. The motor driver has 3 inputs from the Arduino, 2 for direction, 1 for PWM, and 2 power inputs, which are 5 volts for the internal circuitry and 13.4 volts to drive the motor. The shaft of the encoder is mechanically connected to the motor and receives a 5-volt DC signal from the power supply and is used to determine the speed of the motor. The system has two push buttons as input devices and LEDs and an LCD as output devices. Communication between both subsystems occurs using the Bluetooth HC05 module. The figure on the right represents a circuit schematic of the master device with its respective components and an on or off switch. The diagram on the left represents a circuit schematic of the conveyor belt system with its respective components. The figure on the right represents mathematical components used in the system design. The proportional term is proportional to the error. The integral term is found using the trapezoidal method, and the derivative term is found using the backwards difference method. The PID corrected output is the sum of each term multiplied by its respective gain value.
In order to design and construct the conveyor system, that is the slave device, the following objectives were allocated to group members. T. Bihari was tasked with connecting relevant components and soldering where needed, constructing the conveyor system and enclosure, and offered assistance with PID tuning. T. Ramnanan was tasked with pairing the Bluetooth modules used, programming the microcontrollers to receive inputs from the user interface and applying those changes, programming the microcontroller to display information on an LCD, and to debug the final code. K. Jogia was tasked with programming the microcontroller to implement speed and directional control of the motor, implement and tune a PID mechanism via programming, and offered assistance in constructing the enclosure. In order to perform the delegated tasks, the components used were first connected, and the program shown in the flowchart was developed. The program begins with the various variables, including the PID gain values, being defined. The pins of the Arduino that the encoder is connected to is then defined. An encoder function which increases a counter variable for every rotation of the encoder shaft is then defined and called. An internal timer interrupt is then created, which is used to set the sampling time accurately. The program then checks if data is being received via Bluetooth from the user interface and sets the relevant variables to be these user inputted variables. It proceeds to check if the emergency stop button is being pressed and updates the stop state variable, which is entered into a function that is used to stop the motor when the button is pressed. The program then checks if the count variable set by the internal interrupt timer has increased and whether manual mode has been selected or not, thus executing the proceeding code according to the set sampling time of 100 milliseconds. If manual mode is not selected, the actual RPM is calculated by calculating the change in angle of the encoder shaft using the encoder function over the change in time. The error between setpoint RPM and actual RPM, along with a PID corrected voltage to be applied to the motor, is then calculated according to the equations discussed in the design section. This calculated voltage is then bounded to not exceed the maximum voltage of the motor, and the PID corrected voltage is inputted to a motor driver function along with the user-defined direction. The motor driver function converts the calculated voltage to a corresponding voltage level that is between 0 and 5 volts, which is sent to the motor driver, which then supplies the motor with a voltage between 0 and 12 volts based off this. The function is also used to dictate the direction of the motor by activating the relevant transistors in the motor driver's edge bridge. If manual mode is selected, the same process occurs, but the calculated voltage is not a PID corrected voltage and is simply based on desired RPM. The program will then display actual RPM, set point, error, and calculated voltage on the LCD built into the conveyor system. To test the functionality of the motor driver part of the program was loaded onto the microcontroller set in manual mode, and values for set point RPM and direction were entered manually. The serial monitor function was used to view calculated voltage and actual RPM. These values were then verified by measuring the voltage across the motor and by hand counting RPM, and also viewing the direction changes. Preliminary results are shown on the left with manual mode selected. There is no PID control implemented. Time in seconds is shown in the first column, set point RPM in the second column, actual RPM in the third column, calculated voltage in the fourth, and error in the fifth column. The error was quite large and was to be reduced with properly tuned PID control. The Bluetooth functionality was tested by pairing the Bluetooth modules present in the master and slave devices, entering changes in the master device, and viewing if those changes were affected in the slave device. After adjustments were made and changes made in the master device were able to be sent and then received by the slave device, the Bluetooth functionality was deemed successful. The conveyor enclosure, the roller system, and conveyor belts were then assembled using sturdy, repurposed materials, and the relevant components were placed in the enclosure with the shaft of the encoder and motor being fastened into the roller system so that the belt could be turned by the motor and the speed of the belt could be measured by the encoder. The PID gain values were then obtained using a trial and error method of PID tuning, where the gain values were adjusted until a desirable settling time, overshoot, and error was achieved. The results after PID tuning are shown on the right. The error has been greatly reduced compared to when there was no PID control, as shown by comparing the fifth columns of the preliminary results and final results. Settling time and overshoot were also appropriately low. It should be noted that initially a different power supply was to be used, but it was found to be inadequate to power the motor at full speed. Furthermore, sampling time was increased from 50 milliseconds to 100 milliseconds to provide a smoother operation of the belt system. Lastly, the Ziegler-Nichols method was to be used for PID tuning, but due to a lack of data for the motor use, the trial and error method was used instead.
It was the task of A. Abed and Z. Govender to design, program, and construct the wireless user interface for the conveyor belt system. The first task was to create a flowchart to visualize how the user interface will function. It was then determined what components would be required to execute the proposed user interface device. Once the relevant components were chosen, Arduino ports were assigned to the chosen components and a circuit schematic was drawn up. The program for the user interface was then coded on Arduino IDE in accordance with the flowchart. The program was then uploaded to an Arduino and the device was constructed within a plastic housing while making reference to the circuit schematic. At the start of the program, the included libraries are declared and all global variable declarations are made. Thereafter, in the setup code, serial communication is initiated and the input and output devices such as the push buttons and LEDs are assigned the relevant modes and initial values. The program then reads the button states of the stop button and the cycle button. If the stop button is pressed, the stop function is called and a message is sent via Bluetooth to the conveyor belt to stop the motor. If the cycle button is pressed, the count variable is incremented by 1, causing a certain input page to be viewed or the home page. If the count value corresponds to the home page, a message is displayed asking the user to press the cycle button to view or edit the various input parameters. Also, the previous states of the variables are updated and this information is needed when determining if changes have been made. When the count variable corresponds to the mode of operation can be viewed or edited and either manual or automatic can be selected. When the count variable corresponds to the set point or the open loop PWM, these values can be edited by adjusting the potentiometer. When the count variable corresponds to the direction can be viewed or edited and can either be forward or reverse. Finally, after cycling through all the inputs, it is determined whether any changes have been made, and if any changes have been made, the user is asked whether they would like to save those changes. If the user would like to save any changes, they will have to press the confirm button, after which the variables governing the input parameters will be updated and a message saying that changes have been made will be displayed on the LCD. The changes to the variables will also be communicated to the conveyor device. The program then returns to the home page. On the other hand, if the user would like to discard the changes, they would press the cycle button instead of the confirm button, and this will reset the input parameters to their previous values and display a message on the LCD that changes have been discarded. The program then returns to the home page. And if no changes were made in the first place, the user will not be asked to save any changes and the program will simply just return to the home page. It was the task of A. Abed and Z. Govender to design, program, and construct the wireless user. The testing of the user interface was done using the Arduino IDE serial monitor. The block on the left shows results when the input parameters are only being viewed and not edited. The program starts at the input parameters homepage, cycles through all the input parameters using the cycle button, and cycle back to the input parameters homepage. During the second cycle through the input parameters, it can be seen that no changes were communicated. In the block on the right, we can observe the results for the start-stop functioning. The program starts at the input parameters homepage and the stop-start button is pressed, thereby sending a signal to stop the conveyor belt motor with a value of 1 being sent via Bluetooth. The stop-start button is then pressed once more, sending a signal to start the conveyor belt motor with the value 0 being sent via Bluetooth. These results demonstrate how changes are handled. In the left column, changes are made to the various input parameters by toggling the set button on and using the option cycle button and the potentiometer to make changes to the relevant parameters. It can be observed that the changes were successfully communicated, meaning the confirm button was pressed, as when the input parameters are cycled through again, the changes are still present. In the right column, on the other hand, changes were made in a similar fashion, however the changes were discarded, meaning that the cycle button was pressed instead of the confirm button, as it can be seen when the input parameters are cycled through again that the changes are not present. It should also be noted that at first the Easy Transfer library was chosen for Bluetooth communication, but due to its incompatibility with the given microcontroller, it was determined that software serial would have to be used instead, meaning that only one bit could be sent at a time, and that outputs could not be viewed on the remote, as this added functionality required the Easy Transfer library.
Leading communication in the group. Primary form of communication was through social media such as WhatsApp and email. Microsoft Teams was also used to conduct group meetings with the group. Each group member was assigned a specific objective or task. Group members proceeded to inform the group on how they would achieve their individual objectives and communicated their progress regarding their task. Group members informed the group when problems occurred and when changes needed to be made. They first informed the group, then only after approval was given from the group changes were implemented. Group members will also inform the group when assistance was required, and other group members volunteered to assist. Future developments. All objectives and aims have been successfully accomplished. However, the future developments can be discussed to improve aspects of the project. Replacing the Arduino Uno microcontroller with a Raspberry Pi or dedicated programmable logic controller. Implementing a human-machine interface GUI which offers better control and monitoring. Using Wi-Fi for RF communication. Benefits include remote controllability and extended range. Construction of the conveyor material with steel for long-term durability and rigidity. Greater performance motor and rotary encoder with increased characteristics. Adding proximity and photodiode sensors, load cells, and pneumatic actuators. At the end of the presentation, we come to our conclusion. The project constructed fulfills all objectives and can be regarded as successful. Some of the difficulties faced were establishing Bluetooth connection, supplying ample power to the motor driver, and using the Ziegler-Nichols method to tune the PID. This was solved by using different codes to establish Bluetooth connection, using a different power supply, and using the trial and error method to tune the PID respectively.